Start the recording. And today we're going to do a review for exam 1. And so first, let me just pause and say, do you have any questions about anything that we've talked about this week or previous or over homework? No? So I call this review what I would study if I only had an hour. I think it should take way more than an hour to study for this exam. I think that the material, I'll just give you a couple things to think about. One is in class, I tend to do the examples in part so you can see how they're done. One thing that I've learned is that this gives the illusion that it's straightforward and obvious. So I've noticed this when I was a student as well as a teacher, that when I do the work, it seems kind of obvious to the students. And then when they get to the test and they have to do it themselves, it's not obvious. And so if I were you, I would go through the slides and just look at the example problems and act like they're tests and do them without me there and see what questions you come up with. And then you have time to kind of figure it out. You have time to email me. You have time to find classmates. You have time to consult your notes. You have time to review the slides. I really do think that that's a great way of just taking your own temperature on the material, is to go through some of these questions by yourself without looking at the answers. And then the other thing that I've said before is that I think it's really valuable to make a study guide where you go through the slides and you write down all the concepts, all the formulas, and you explain the concepts and the formulas to yourself after you've read and understood everything that you can from the slides and from the text. Those, I think, are the kind of the two best ways of preparing yourself for the exam. So the question is do you have an idea of what formula sheet to make for ourselves? Just off of the top of my head, I would have the mean, the median, variance, standard deviation, covariance, correlation, the summation properties, the variance and covariance and correlation properties that we talked about, I think, at the end of Deck 3. The formula for beta naught and beta 1, the first order conditions, which are basically that the expected value of all the errors will be 0, and that the errors are uncorrelated with the x's. But I would just go through the slides and I would write down every formula there and feel like you understood what the formula was doing, what's going on the right-hand side of the formula. And what is it measuring intuitively? It'd be really good to kind of think through for instance, in the variance, you're always measuring the distance between all the data points and the mean. So essentially, if all the data points are close to the mean, the variance will be small. If all the points are far from the mean, the variance will be large. So really, the variance is measuring how spread out the data are away from the mean. That's kind of just one example, but but there, of course, are many, many others. I'm not sure if it's included in the review already, but could you go over how correlation and covariance are different? Yes, I think we will do that today. And if this deck doesn't, which I think it does, we will get back to it at the end. Let me just write that down for myself so I don't forget. Difference between correlation and covariance. I just uploaded the lecture recording from yesterday, so that is available. And Let me fill up my water really quick. I'll be right back. Okay. So, and one thing that's also true in reviews is that sometimes it feels like you have, there's just like so much to review in a review that it feels overwhelming. Often when you go back and you actually look at the materials and you have a little list of yourself of all of the concepts, and you're able to go through them at a natural pace for someone, um, for yourself, then it isn't as scary. So sometimes reviews, just because they're at such quick pace, because I'm trying to provide you all the information, I think we'll be able to cover probably 70% of the information that could possibly be on the exam in 1 hour. But that means that we might go a little bit faster than is totally comfortable. So a regression line, and all I mean to say by that is that that's totally natural. Don't feel overwhelmed just because we're covering a lot of ground. The income of individual I is a function of his or her years of education and a random element. So this is just our basic kind of regression setup. We have an outcome variable on the left, we have explanatory variable or variables on the right, and we're estimating parameters, beta and beta naught and beta 1, that minimize these errors, where these errors are the distance between the data points and our regression line. In this class, we've learned how to compute beta naught and beta 1 so that we have an equation like the following, which is the income, predicted income. Remember that we know that we're talking about income that's predicted and not that's in data. If the variable on the left has a hat, income hat could be 10,000 plus 1,500 times the number of years of education. So what does this mean? Does it mean that education increases your income by 1,500 per year? Not quite. It means that on average, people with an additional year of education earn $1,500 more per year of education. That could be because of selection. It could be because there's a causal effect of education, but this is just the average relationship between the two. So a simple question might be, what's the income that you would predict for someone with 0 years of education? All you would do is plug in 0 years of education into the formula and you'd get 10,000. Or I could say, what's the predicted amount of income for someone with 10 years of education? And you might say 10K plus 1,500 times 10 years of education. That's going to be 25,000. Okay, et cetera, et cetera. I could also say I have someone with a predicted income of $40,000. What is the level of education that that person likely has? And then you would just plug in, whatever this is, 40,000 into the formula. And solve for education. So first you'd subtract 10K off of this side and off of the right and the left, and then you divide both sides by 1,500 to find out how much education you would need to on average, have an income of $40,000. Okay, questions there? So what are we trying to do with regressions usually? There's usually a few purposes that we have. One is to test hypotheses. So we can establish if the relationship between education and income is positive or negative, if it's zero, if it's strong or weak statistically. We haven't gotten to statistical significance yet, so it's just about testing hypotheses in which the coefficient is either usually positive or negative or zero. We can also make predictions. So we can predict a person's income given his or her level of education, for instance. And finally, we can try to establish causal relationships by arguing that education causes income to increase. Basically, we have to make the case that people with more or less education are equal in every other regard that affects wages. So they have to have the same work ethic, the same family structure, the same the same amount of experience, the same amount of brightness. Just every other thing that might affect your wages needs to be the same among people that have high and low levels of education. So ceteris paribus is really the core of the causal claim. When I say that I think that the coefficient on education reflects a causal effect of education on wages, what I must be able to prove or believe is the ceteris paribus assumption, which is that all of the things are being held equal or constant. So just as we said in the previous slide, what that means is we have to be able to believe that people with more education are the same in every other respect to those with less education. So if we find that people with more education are taller or from more driven families or have higher IQs or work longer hours or any of these other things, or have or gain more experience or work more in high school, or did have any other differences, we can't argue that relationship is totally causal. It has some sort of selection in it. People that have more education are different in other regards. So we have that kind of written out here. We need to assume that individuals with more education have identical ability, family resources, motivation, etc., which is not likely to be true. So when we, as real economists, are trying to measure the effect of education, we're looking for places in the world where similar people are receiving different levels of education. So one example would be, say there was a scholarship, and if you got a 1400 on your SAT, you got the scholarship. And if you got a 1390 or below, you don't get the scholarship. We could compare the people that got the 1390 to the people that got the 1400. So these are people with basically very similar scores, almost, it's kind of whether they bubbled in an additional question right by accident at the end of the test, whether you got a 1400 or 1390. So these are people, these two groups we think are actually probably similar in terms of their ability, their family resources, their motivation. But a person that got a 1400 has a scholarship and might be therefore more likely to go to college. And so what we could do is compare the people that got the 1390 to the people that got the 1400. And there would be a nice argument that this is actually causal. Questions there. So that's a really important piece of just the class. That's probably this and omitted variables bias are actually kind of the same thing. They're related. Cameron, Danielson, Derek, Devin, Esmeralda, Ibrahim, anything? Okay. Awesome. So there are different kinds of data that we sometimes think about. The simplest and probably most common is called time cross-sectional data. So this is data where we have multiple people in a data set, and we observe them each at one point in time. So the most common data is called the Current Population Survey in the US. And it basically, the US government surveys 160,000 people every month and basically asks them their age, their race, their gender, their whether they're employed, whether they're looking for work, and a few other things. And the primary purpose of that data is to calculate the unemployment rate. And so this is cross-sectional data because we have many individuals in the data, and we observe each of them just one time. We observe them in March 2017 or in January 2005 or whatever. That survey doesn't ask the same people over and over again, so it's a cross-section. We just see every person at one time. Another kind of a more basic data set, we'd often see this in terms of unemployment rates, is time series. So we'll see what is the unemployment rate over time for a given country or a given state, or sometimes a given industry. Or we might have if you have like a smartwatch, we could imagine plotting your heart rate over a long period of time. So it's going to go up during the day and down during night, and up whenever you're exercising and down whenever you're relaxing. And because we see one individual over time in this kind of data, it would be called time series. And then the last kind of data is sort of what economists often use because it allows us to do some really nice controls, is panel data. So panel data is where we have multiple people and we observe each of these multiple people over time. So maybe I have a panel data set made of students in this class where I see each of your course enrollments in every semester, or your GPA in every semester that you're at school at UC Merced. So those would be considered panel data because I have multiple individuals that I can follow over time. And importantly, in each of these, the unit of observation, I've been using examples where the unit of observation is a person. It's very common for these data sets actually to not be in terms of people, but in terms of firms or companies or countries or counties or employers, cities. All of those would be kind of typical places that we might have. In each case, those could also be cross-sectional data, time series data, panel data, depending on when and how many people we see them, when and how many we see in the data. So if it's multiple countries over time, that's still panel data. Okay, sampling. So in order to make if we wanted to know what the unemployment rate was or who will win the election, we don't have the time or the resources to ask every single person in the country whether they're employed or, excuse me, or who they're going to vote for. So what we usually do is we use a sample, and we can actually find very accurate um, estimates of the populations, how many of them are independents or how many of them are unemployed, using sampling. So a random sample is kind of the gold standard. A random sample is one in which every member of the population is selected to be part of the sample at random. What that means is that some people aren't more likely to be sampled than others. So if I'm sampling outside a grocery store, or I'm sampling at UC Merced, or I'm sampling people that have landlines, these are not random samples because I'm asking a group of people that is potentially different than the rest. So for instance, people that are at the grocery store, I'm not going to ever talk to people that don't grocery shop or they get their groceries, or I might be more likely to speak to women than to men, for instance. At the gym, I might be much more likely to speak to athletic or healthy people than sick people or people that are not in good shape. At UC Merced, I might be much more likely to talk to people that really value their education than people if I just talk to a random person in the street. And that's not to say that every single person in those groups is a woman or is healthy or is very interested in their education. It's just that the average person in those samples might be different than the average person in a truly random sample. So random sampling is quite difficult to implement in practice because you need basically a universal registry of people. And then from that, you randomly select who to contact. So whenever you don't have a perfectly random sample, you have something called selection bias, where those that are selected to be in the sample are not fully representative of the population. And so this is what we call this is kind of the researcher's error. This is a limitation of what the researcher is doing. On the other hand, we have, even if we were really lucky and we had a random sample, I could imagine having a random sample of UC Merced students. The administration's office has a list of all the email addresses of all of the students at school. We could literally randomize which students are invited to take a survey. So that'd be a perfect random sample of current UC Merced students. Then what we have to worry about is response bias, which is that we're unable to collect data for basically the response bias is the fact that some people are more likely to respond to a survey than others, and that those differences might also represent selection. So typically you might think of people that are really lonely as really eager to answer the phone and talk to a stranger for a long period of time. There are these kind of in one of the criticisms of the political polls that were very off in 2020 was that, like the kind of clever, I want to call them sexy polls. They're kind of smart polls. They would ask you one or two questions by text. So it's very easy to respond. You're not very quick. You can respond at any time in 2 days. So if you don't have time right this second to respond to the poll, that's okay. And there's no person on the other, you're not like talking to an individual, you're talking usually to a robot. And often when you talk to an individual, you feel pressure to believe certain things or to say certain things. So we call that's called interviewer bias. Basically, you might change your responses to be kind of socially acceptable to the person that you're speaking to. So sometimes that's where by misrepresentation can come in. Then some of the other polling institutions, namely some of our really kind of older polling institutions like Gallup, they were having 45-minute polls on the over the phone. So you can imagine that if someone called me and said, "Can I speak with you for the next 45 minutes?" I would say, "No, I have a job and I have kids and the yard and my grass is dying." But if I were maybe an 80-year-old person and I'm retired, I don't have anything going on, I live in a community where I don't need to take care of the lawn, I might have endless time to talk. So what is the kind of person who is selecting into a survey who has the time to take a 45-minute survey talking to a stranger? Okay, so this is response bias. That would kind of exacerbate response bias. Is that the people that are responding to the survey are not representative of the group? They have something sort of special or different about them. Okay, questions here. Devin, Esmeralda, Ibrahim, Katrina, Kimberly, Manuel. Okay. Okay, sounds good. So we did these in class and we did the homework together. So I'll be quick for this, but basically the population is always all the groups in this that we would want to have information on. So that could be all UC Merced students, all cities in the US, all companies in California. A sample is a selection from the population. So we could talk to 100 students at the library. We could try to sample all the cities in the US that begin with a C. We could have a selection of companies with at least 50 employees. So these are all just different samples. They're not good samples. They're not random samples, but they're all ways of finding a subgroup of the population that we're interested in studying. Okay. So we've got two common data distributions that we've talked about. One is uniform, where every value in the data set have this equal probability. So the classic example of that would be a dice. If you're rolling a dice or flipping a coin, each of the possible outcomes of that roll or that flip are equally likely. So the test is roughly ordered. Someone asked, is the test going to be in order or mixed? It's roughly ordered, but there's some jumping back and forth. But yeah, there is kind of like, you'll notice that two questions will come up about the same topic and then it will change topics or something like that. So there is a little bit of kind of progression in it. And then, but it's not kind of total, it's not completely ordered. So the second kind of distribution that we often see is called a normal distribution. And a normal distribution is just something is where there's a bell curve. Okay. So it means that there's to say this were the middle. Say that were the middle. It means that there will be a lot of mass in the middle and that there will be thin tails that kind of. So normal is small, the tails are small, the middle's fat. Is a normal distribution. It's very common in nature, in part because extremes are cut down in nature. So if you're, very, very tall person, it would have been hard to sustain yourself. If you're a very, very short person, it would have been hard to defend yourself. And so in nature, we see these bell curves where there's kind of this Goldilocks part where you're just kind of, what's this called? You're kind of tuned to your environment in the middle. There are many data distributions. We're going to use mostly normal and uniform. And many variables do not follow any normal or any distribution that we have kind of an equation for. But these are normal is very common actually, but some distributions don't follow something kind of ordered and pretty like a normal distribution. So these are all actually normal. They have different means. The mean of a normal distribution is where is the middle. Okay. So which has the higher mean? No, let me do this one. Which has the higher mean between the yellow curve and the green curve? Which has the higher mean? Actually, let me do it this way. Which has a higher mean, the green curve or the red curve? Okay, let me make a poll really quick. Let me see if I can make a poll here. For some reason, it does not like that I'm logged in here as well. Okay, can we just have it in chat? Who thinks that which curve has the higher mean, the red curve or the green curve? Okay, you all nailed it. It's the red curve. The blue curve also has a higher mean than the green curve, but the red or the green. So the important thing is that it's important to just think through what these axes are. So the X is the value in the data. The Y is how common that value is in the data set. So this is a kind of a tricky question where you might think that the taller distribution has a higher mean, but the height of the distribution just means that the data are more concentrated. So this blue figure here means that the values are all concentrated in the middle. That's why almost about looks like 90% of the values in this blue data variable are at 0. So almost 90% of the data are right in the middle. But the average is the X over which the middle stands. So the middle here for blue, red, and yellow are all, the average is 0. X bar for yellow, red, and blue are all 0. The average for the green is -2. Okay, so that's we have 3 ways of kind of calculating where is the middle of the data set. We have the mean, the median, and the mode. And those are probably pretty familiar to you just over years and years of exposure to those concepts. Probably a little bit less familiar is spread. So we have 2 measures of spread. Spread is just how concentrated is each variable. You can see that this yellow variable is super spread out, right? And this blue variable is super concentrated. All of the values of this blue variable are very similar to one another. Okay, and this yellow variable is super spread out. So that's a measure. We have a measure just to figure out how spread out those are. Questions? Okay. So the measures of central tendency, as we said, were mean, median, and mode. Just to state those really quickly, the mean is the sum of all the values in the sample divided by the number of values in the sample. The median is the value that separates the higher half of the data from the lower half of the data. And the mode is the value in the data that happens most often.
Wait, were you talking about that car? Yeah. Oh, hi. My name is.
Hi, Kimberly. We're getting some background noise from you, I think.
Okay, let's get you started.
Let me see if I can.
I am.
Pay for it?
What?
Are you doing this to help like pay for everything?
Yeah. It's helping me save up. I actually have to live off campus because housing is limited because of COVID. So I'm pretty sure they made like 3 new buildings last year, but I don't think they're going to use them to full capacity.
Okay. Okay, so our main measure of spread is called variance. And variance, you can think of it as how much does something vary? How much does something differ? How much does a variable differ? How much do the data points in a variable differ from one another? It's computed by taking the difference between each number and the mean, squaring it, and then taking the mean of these squared values, where larger values correspond to a wider spread. Okay, so all we're doing, the sample variance will be 1 over n minus 1. So 1 over 1 fewer than the sample size. And then all we do is we calculate the distance between each data point and the mean, square it, and take the sum of all of those distances. Okay. So the standard deviation is actually the exact same calculation, except we add to it by taking the square root of the variance. So all it is the square root of the variance. Okay. Covariance is, instead of we're not now trying to figure out how much spread there is in an individual variable. We're trying to understand how 2 variables move together. So all we do here is we'll find the distance between x and its average and multiply it by the distance between that y, the y data point for that x, that y's value, and y's average. So what we'll find, for instance, is that if when there are large x's, there are large y's. We'll have a positive value here and a positive value here. So the product will tend to be positive. If for large values of x, we instead find small values of y, we will have that the correlation, the covariance will instead be negative, because the product of a positive and a negative number is a negative number. And then, of course, if we have that, when we have small values of x, we have small values of y, we'll find that this reflects a positive correlation, because a negative times a negative is a positive. And then it could be that when you have larger values of x, you have neither smaller nor larger values of y. And this will tend to give us a covariance close to 0. If larger values of x have no larger or smaller values of y, we'll have a covariance of 0.
Professor?
Yeah.
For the covariance, does it have to be x1 and then x2, or can you multiply all the x's together and then all the y's together and then add them up at the variant? Or does it have to be x1, x2, or x1, y1, and then x2, y2? Do you understand my question? Or?
Yes, I think so. Is it that you have to multiply x1 minus x bar times y1 minus y bar, or could you do x1? Can you hear me?
Oh, yeah, now I can. I think you're frozen.
sorry, my internet connection is apparently unstable. That's what my Mac just told me.
Sorry.
Let me just check and see if I have weak connection for some reason. I'm gonna plug, sometimes my internet is, let me just plug one thing in here. Oh, there it is. So is the question, do you have to multiply x1 minus x bar times y1 minus y bar? Or can you instead do something else? Is that the idea?
So like, so basically it's just the x1 minus the x bar, and then the y1 minus the y bar. You multiply those together, and then you add it up with all the other x's and y's, right?
Mm-hmm.
All right.
And I think your question was, can you do x1 minus x bar times, you were asking, can you do all the x's and then all the y's?
Yeah, so if we were to do like all the x's and add all the x's together, and then all the y's and add all the y's together, and then just add them up at the end, or would that not work?
No, it doesn't. Unfortunately, it doesn't work like that, just because you're actually calculating how each individual data point, its x and y value are related. So if you summed up all the x's, x distances, and then you summed up all the y distances, or you multiplied them, you get a different value. And that is, that's a really good question that I feel like I'm not explaining very well. Let me think if I can think of a good example that would kind of clarify that. But you can also just pick any data set that we've used and do the two numbers, and you'll just find that you get different values for those two calculations. They're not equivalent.
Oh, thank you.
No, great question. Thank you. Okay. So sometimes we want the covariance to understand the relationship between two variables. Often we will want to instead consider the correlation, which is going to give us something that's kind of easier to interpret. So where the covariance is going to be some number that could be 12 or 40 or 1, and we actually don't know very well what that means, the correlation is going to normalize the covariance by dividing by the standard deviation of x and the standard deviation of y. So we're basically going to account for the fact that how spread out x and y are. And I'm sorry, my other stylus broke down. It didn't break down. It ran out of battery. So I'm back to my bad stylus today. I'm sorry. So what we're going to get from this correlation, from this formula, is we're going to get a value, which is, actually we write it this way, a value which is somewhere in the set between -1 and 1 inclusive. So a -1 is a perfect negative relationship between x and y. A +1 is a perfect positive correlation. So what would those look like in the data? If we had something like this, where the points are basically in a straight line, this would be a correlation of -1. If we had data that were basically in a straight line, any positive slope, we would have a correlation of +1. In general, we have data sets that look like this. And this would be a correlation of just guessing, it'd be a correlation of 0.3 or something like that. Okay. So it's basically how well does the data fit into a line. So I would definitely, going back to Noah's good question, I would definitely know these formulas: correlation, covariance, standard deviation, variance, mean, median, and mode. Definitely. I don't think there's been any other formulas yet. Okay, let's take a little break. I'm gonna share this is a really funny comedian who I enjoy, called Anthony Jeselnik. Have any of you ever had a friend called Feliu? F-E-L-I-U. I have this great friend, Filio Serra Buriel. I think he's from Spain, but I didn't know if it was like a Spanish name or a Catalonian name or what. Filio. Thought it might be related to Felix, but I think Felix is I have Hispanic friends called Felix. Okay.
All right, guys, listen.
Okay, so I'm sorry. Let me just
These are all well and
explain.
good. I'd like you to take a couple minutes right now and talk about something that is important.
Sorry. So let me just explain what this is. This is Anthony Jeselnik. This is part of his Netflix, one of his Netflix specials, and he plays kind of a Satan character. And his joke construction is really, really good. So I hope you enjoy this for a little break minute. Just one. And I'm sharing my screen, right? Let me see.
Yes, you are.
Okay.
All
right. His whole special, he has 2 specials on Netflix, and they're both like some of the best writing in comedy I've ever seen. Fire in the Maternity Ward, and I can't remember the name of the other one. I have a baby. I don't endorse dropping a baby. It's a joke. It's a joke. Okay. Okay. So that's that. Any questions so far? No? Okay. We'll power on. So back to Noah's question, what equations or what formulas are good to know? I would know these formulas, that when you sum a constant n times, it's equivalent to multiplying the constant by n. When you sum a data variable, it's equal to multiplying the average of the average of that data to how many data points there are. When you are summing an xi multiplied by some constant, it's the same as pulling the constant out of the summation. And finally, when you are taking the sum of parenthetical sum, it's equivalent to breaking that summation into 2 parts. So what this one really means is it doesn't matter what order in which you add things together. You can add the x's and the y's together and then sum those sums up, or you can sum all the x's and then all the y's and then sum those sums up. Those are equivalent. This one is really about this one right here. is really about the fact that when you multiply one number by everything in a sum, you can factorize that number out and multiply and add all of the unfactorized pieces together before multiplying it by the constant. The insight of this one is that if I give you the average, so say I said the average American earns $60,000 and there are 330 million Americans, you could calculate the whole income of the country based on that. And this one is, I would call it kind of trivial. It's just if you add C plus C plus C plus C, C plus C plus C, it's the same n times. It's the same as just multiplying C by n. Okay, here are some properties of statistics that can be really helpful. They're related. So based on these formulas up here, you could prove each of these, but I'm not going to ask you to. So here we have that the mean of C times a variable is equal to C times the mean of that variable. Here we have, when we have C multiplied by some X, and we're taking the variance of this new variable C times X, it's equal to C squared times the variation in X. Sorry, that's a bit of a mess. When we have the standard deviation instead, it's just C. So basically when we pull out a constant from a variance, it becomes squared. When we pull out a constant from a standard deviation, it just remains itself. It doesn't need to be squared. And I'm guessing that you've seen these before in different ways. This is a great one. The covariance between X and some constant is always 0. So X can't vary with a constant. If I, and that's easy to see. I can show you that, like say we had X is X is 1, 2, 3, and the C is going to be constant. So it doesn't matter what it is, but it's going to be maybe 1, 1, and 1. When we do the covariance for this, what we're going to have is 1 minus 2 times 1 minus the average of C is 1, plus 2 minus 2 times 1 minus 1, plus 3 minus 2 times 1 minus 1. So what do you notice is that we're always going to be multiplying the the first term by a 0. And what all that means is that you can't have any covariance between X and a constant, or Y and a constant. X has to be, X will only covary with another variable, not with another constant. Here is another one, basically the same idea as before, as we can pull a constant out of a covariance. If we calculate the covariance between X and X, it's identical to the variance of X. And you can see that even if you just do the formula for the covariance between X and X is identical to the formula for the variance of X. Okay. Okay, so here's some more good, these are really good things to just have under your belt. So Y is the outcome variable, X is the explanatory variable, beta naught is the y-intercept, beta 1 is the slope of the relationship. So we've seen that before many times, and so that's just worth kind of making part of you. Okay, when we're calculating, so I think there is a question where I ask you to calculate beta naught and beta 1. The formula for beta 1 is covariance between X and Y divided by the variance of X. And then beta 1 can be calculated, beta naught, I'm sorry, can be calculated by the average of Y, excuse me, minus beta 1 times the average of X. Remember that X, whenever we bar something, Y bar and X bar are the mean of the two variables. And note that the beta 1 is the slope, while beta naught is the y-intercept. So we've seen that before. So deriving OLS, I don't think I'm going to ask you to derive OLS, but there are two little things that are kind of intuitive about this. I think I might say, what's the, if you did derive OLS, what would you do? And all you're doing is taking the sum of squared errors and minimizing it. And to minimize, you take the derivative of the sum of squared errors with respect to beta naught, beta 1, and set it equal to 0. So that's kind of the magic. By setting it equal to 0, we find the beta naught and beta 1 that minimize the sum of the squared errors. That's really what we're doing. Two cool insights from this are that this means this first order condition means that the sum of the UIs will be 0. And this means that the sum of xi times ui will also be 0. So that's really cool. That means that we're going to select beta naughts and beta 1s that make the sum of all of the UIs 0, and that make the relationship between the UIs and x also 0. Okay, so if you want to know what's the predicted value, so this will definitely be a part of the exam. I'll give you a regression and then I'll say what's the predicted value for education equals 10 or something like that. And all you'll do is plug in that education equals 10 into the estimated regression equation. If you want to know what the effect of some x on y is, take the derivative of y with respect to x and plug in any values, squared terms, interaction terms, etc. So when we say what the effect of some x on y is what we want to know is what's the marginal relationship between an additional unit of x and the outcome variable. So we've done a couple examples like that. Just a really quick one, and say we had y, oh bother, y equals beta naught plus beta 1 education. And you, this is just a very simple example. And I asked, what's the marginal effect? What's the marginal relationship of an additional unit of education on y? You could take the derivative of y with respect to education, and you would get 0 plus beta 1. So for 1 unit additional of education, you'll get a beta increase in y. Okay, the relationship we want to estimate, and this is the same example as actually I just did without even knowing it, is we have a regression equation, we have a predicted prediction, and then to interpret beta 1 as a derivative, we'll take the derivative of wage with respect to education. And okay, sorry, my screen share stopped for some reason. Let's see if it's working. Okay. And we get beta 1 is the marginal effect or the relationship between education, an additional unit of education and wage. Okay, so often we'll have data and we're interested in knowing how well our data are fitted by the model that we've estimated. And if the data are spread out, so this is just really just kind of basic. So say we have 2 data sets In one, we've got this really nice tight relationship. And in one, the data are just kind of everywhere. Boop, 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 boop. So when we find that this model fits the data really well, and this model doesn't fit the data very well, but there's not a better model. So that's one thing that is just true about regressions, is that when we're using ordinary least squares, we're using the line that maximizes the R squared. By minimizing the sum of squared errors, we are maximizing the R squared at this exact same time. So it's when I say that this model doesn't fit very well, it's not that there's a better model out there. It's that this is the best model that we can estimate for these data. It doesn't fit well. They're just the data do not fit our model well, and there's not much that can be done about it. So to calculate the R squared, we calculate the sum of squared residuals by summing up the square of each y value minus its predicted value. And the sum of total squares is just the sum of, is basically the variance of y, is equal to the variance of y. Variance of y. So it's just each y value minus its average squared, and then summing all of those squares up. So basically, consider this example right here, where all of the data points are very close to the line. What that means is that this value is going to be small. The distance between the y's and the predicted values is small. And the variance in y is actually still pretty large. Actually, the variance in these two figures, the top and the bottom, will have a similar variance of y. But we'll find that the SSR is small, divided by the SST, which is pretty large, will be a small number, equals a small number for this top example. So when we calculate the R squared, and it's 1 minus a small number, we'll get actually a number that's pretty large. It might be 0.9. 0.9 is that it's a very tight fitting regression. And then, so say we did, so try to just keep that in your head. I'm going to just delete this so that if we instead did the SSR for this figure down here, we would find that the SSR would be big. There's lots of distance between the data points and the line that we're fitting. So when we, so our SSR divided by SST for this bottom example would be pretty large number. So when we calculate the R squared here, it might be something like 0.1 or maybe even less, 0.02 or something like that. Okay. And notice that SSR is always at, SSR can be no greater than SST. So the R squared is a value that will always fall between 0 and 1. Where a large value of an R squared means that the regression is fitting the data very tightly, and where a low number means that the regression line doesn't fit the data very tightly at all. Questions here? So the variable scaling, we saw that when we change the scaling of the X or the Y, it affects our betas. And all that means is that we have to pay attention to the units in our data to appropriately interpret what the beta means. So say I think one of our examples was, say we had initially an X, where X is the number of feet you are tall. And we're interested, if we multiply X by 12, constant called 12, we get height in inches. So initially we estimated this beta 1 hat using X and Y. And our question is, how different will the beta hat be when we use height in inches rather than height in feet? And the answer is that we'll actually find a value that is the old value of our beta, our original value of our beta 1 divided by the constant that we multiplied X by. So it's 1 over 12 times the old beta will be our U beta. And the constant term, the y-intercept, doesn't change because it actually doesn't matter how much you spread out or contract the x-axis by. The line is going to always intersect the y-axis at the exact same point. So one just like thing to think about is, so when in our height example, it's as if we're stretching out the x-axis so that it's larger, it's 12 times larger. So what that means is, say we were interested in the relationship between height and wages. Now, what we originally had was a relationship between a 1 foot increase in height and your wages. But now there are 12 unit increases instead of 1 increases. So a 1 foot increase is the same as a 12-inch increase. And what that means is that as you're spreading out, if you just imagine like a figure like this, where the x is here, if we spread out x, it actually needs to make the slope less steep in order for the data, the line, to keep going through the middle of the data. I'm just trying to say it in a couple different ways so that if one of them clicks, that's great. If it doesn't, that's totally fine. But the idea is, if we have the exact same line and we were making X more spread out. Oh, another idea is, say we were, instead of measuring feet in height in feet, we were measuring it in kilometers. So we're going to make the x-axis very small. That one unit increase in feet is in height is in the units of kilometers. So this is going to tend to make the slope of that relationship very, very tall. I'm sorry, I lost my screen share again. Okay. Okay. So the other was where instead of multiplying X by something, we're multiplying A by something. And here what we find is actually when we scale the Y variable by A, our new beta 1 will be A times the old beta 1. And our new intercept will be A times the old intercept. So that's actually, in some ways, just kind of more intuitive. When I scale Y by some variable, the slope has to change to fit the new variance in Y, and the intercept has to change to fit the new place in which the slope is intersecting our Y-intercept. So when an outcome Y is scaled up, both the slope coefficient and the intercept are scaled up by the exact same amount. Any questions here? Hopefully this feels like a dream you've had before, you know, like, oh yeah, I've seen something like this before. So this is a useful one. So this is something, so say we have binary levels. Oh, I see. Y here, when I have binary, I forgot how I had written this. Binary levels means that Y is binary and X is not binary, it's in levels. So what this means is that for a 1 unit change in X, there will be a beta 1 increase in the probability of the outcome. So say the outcome were graduating from college and X is your SAT score. A 1 point increase in SAT score would have a beta 1 impact on the probability of graduating, for instance. This is levels binary. So that means that the outcome variable is in levels. So maybe this is your SAT score, and the binary variable is whether you did a test prep. And so what we find here is that the beta 1 on this regression would be how different are test scores between people that take test prep and people that don't. And finally, if the outcome variable and the X variable are both binary, so say this is the effect of taking test prep in high school on your college graduation, it would be people that took test prep are 4 percentage points more likely or less likely to graduate from college, whatever the case may be. This is just useful for kind of, I'll give you maybe like a regression equation and I'll ask you to interpret it. And sometimes these examples are really helpful. Okay, multivariate regressions. So what do these do in short? What beta 1 is measuring is the change in Y with respect to X while holding X2 fixed. So essentially what that means is for people with the same level of X2 and different levels of X1, how is Y related to X1? It's a similar thing for beta 2. Beta 2 is the change in Y for a change in X2 while holding X1 fixed. Okay. So here we have, sometimes the data are curved. I think our example, I'll do a slightly different example than the one that we saw before. Could be that the data look like this. Okay. So if we try to fit a straight line through these points, it's just going to do a bad job. We're going to be over predicting here. We're going to be under predicting here. It's just not going to do a very good job. So often what we'll do is we'll include a squared term of whatever our X variable is. And that's going to allow us to fit some curvature in Y with respect to X. So in this example here, what sign does our beta 1 have? Our sign will be something positive. Remember that the beta 1 is the slope at the y-axis, and our beta 2 is the second derivative. So here the second derivative is just how does the slope change as x2 increases. The slope is getting more positive as x increases. So the beta 2 will also have a positive sign in this example over here, not in this example up here. Okay. Okay, so you could take the first derivative of wage with respect to experience, and you'd find this. And I might ask, what's the slope when experience is 2? What's the slope when experience is 10? So this is basically how much does an additional year of experience affect your wages when you have a small amount of experience or when you have a large amount of experience. And those will be different because we've allowed for the curve, they can be different because we've allowed for the curvature to differ over X. Okay, this is a really important piece. I don't know why this is called omitted variables. So whenever we have a regression, So say there's a regression of y equals beta naught plus beta 1 x1, and we think that there's a variable we couldn't measure, we don't have in our data set, that is related to, correlated with x1 and affects y, then if that's true, then beta 1 is biased. Biased means that the beta 1 that we're estimating is not the causal impact of x1 on y. Okay, so if either of these relationships are broken, then it can still be causal. So say x2 affects y, but it's not correlated with x1. Then there's no omitted variables bias. So for instance, say that actually I think we'll have an example in a little bit, but you can think of all sorts of examples in which x2 will affect y, but it's not correlated to x1. The other is if x2 is correlated to x1, but it doesn't affect y, then also we don't have an omitted variables bias problem. So like I think the example that I had before was one time was, so say wearing a wristwatch is correlated with education, but wearing a wristwatch doesn't have any effect on your earnings, then there's not omitted variables bias by not controlling for wearing a wristwatch. Wristwatch is a hard thing to say. Wristwatch. Okay. So the basic way that we can measure how much bias there is basically the beta that we're able to estimate will be the true beta plus this term, where this term is beta 2 is the effect of x2 on y, and delta 1 is the effect, is the slope of x1 on x2. Okay, so notice that if either of those are 0, if x2 doesn't affect y or x2 is not related to x1, there's no bias. Okay, there's no bias. And using this nice term, we can figure out what kind of bias we might be facing. So say we have an omitted variable that has a positive effect on wages, and the relationship between this omitted variable and our y is positive, we expect that the bias that would produce would be positive. If we have, again, a omitted variable that has a positive effect on the outcome, but it's negatively related to x1, then we'll have a negative bias. Why is that? All we do is we're putting this into our formula where we have beta 2 times delta 1, where we have a positive value for beta 2 and a negative value for beta 1, which is going to be a negative value. So the bias will be negative. We'll understate the effect of x1. Okay. Okay. This is our last topic for today. We'll have two. This is actually what we did most recently, which was interaction terms. So say we have experience and we have education. We want to see how they interact to affect wages. We can simply make a third variable in which we multiply each person's experience by their education, and that will be a third variable called an interaction term. And all this allows us to do is have the effect of education depend on experience and the effect of experience depend on education, so that the effect of either of these varies with the other one. So we just did these examples yesterday. I'm not, and we're basically out of time. Yeah, we did all of these yesterday, and we did all of this yesterday. So let me stop and take questions, and yeah, let's do that. Thanks for being here. This has been a really fun class for me. I like you guys a lot. I don't think that the test is going to be hard. I think you have all the tools that you need to prepare for the test, and that you'll be glad if you take a good chunk of time and really settle into the material. And yeah, I just think like everything in the second half of this class will be easier if you do. You'll find that you'll learn things in the exam if you're prepared, and things will start to connect better if you've really prepared for the exam. And honestly, I think this is a really great class. I think if you go into government, if you go into private industry, if you go into academia, if you run your own business, I'm teaching you tools that you can use to make your business or your government or your company work better. And so I really do think that this is something that's worth your time. It's worth some effort. And yeah, and feel free to email me tomorrow. I won't be around very much over the weekend. I'm on dad duty during the weekend, but I'm happy to meet and talk and answer questions tomorrow. Yeah, I think you're going to do great on the test, but I really do think it's worth it. It wouldn't be something where I'd suggest not doing a lot of prep, but it's everything that we've done. There are no surprises. There are no just no twists. I don't think. I really wrote this to be as straightforward and simple as possible. But there is kind of a trick where when we do things together, it looks obvious, it looks clear, and it feels different when you're doing it alone for the first time. So I really encourage you to try to do some examples tonight so that we can talk about them tomorrow. And yeah, and also, if you guys want to study with each other over Zoom, put your email addresses in the Zoom chat so that the other people that want to study together can find you. Yeah, that'd be great. So I have a comment about the quiz. Yes, Kimberly.
So I think it was question 3 or 4. It was about covariance. So I clicked none of the above because one of the answers was covariance is like looks at two variables and looks at how two variables move together, right? But I felt like that answer wasn't sufficient because it's not just how two variables move together, it's how they move in relation to each other. So that's why I feel like I'm refuting that answer. Does that make sense?
Yes. Let me look at it really quick just so that I don't.
I'm not looking at it right. I'm sorry. I'm not looking at it right now, but I just remember the words.
No, I'm sure you're right. It's just sometimes it's helpful for me to see it in writing.
Yeah.
Okay. So it says the correlation is a measure of. Is that the one?
Yeah. Okay. Correlation. Yeah.
Is a measure of how two variables move together, the central tendency of a variable, the spread of a variable, no answer text provided. Mm-hmm. Is that the one you selected? No.
Yeah, because I felt like how they move together just wasn't enough. I really had to think about that. I was looking at my notes when I was doing it, and I felt like that wasn't enough. It's how they move in relation to each other and like studying that relationship that they have, not just them moving together. Does that make sense?
Yeah, I get you. So I think let me go back into my notes and check it. I think that was the way that I described it in the slides, is that it's a measure of how two variables move together. And what was it you said that was slightly different?
It's not just how they move, it's how they move in relation to each other, like the relationship between those two variables. It's not just how they move in the data.
Yeah. Yeah, let me think about it a little bit. I think that the moving together is kind of the same idea. It's how they're
I felt
related,
like it
how they
wasn't.
move together. And let me check and see what I have in the slides. If I
Okay.
said something, I might have written something that threw you off. Let me look into it a little bit.
Okay. Because I know, like, I understand the question and I had to like really think about it. And I was like, well, moving together really doesn't cover it. So I'm not going to select that. And yeah.
No, thanks for bringing that up. I would not have thought of that, and let me look into it a little bit more.
Okay.
Other questions? And Kimberly, thank you for bringing it up. It is very helpful for me to just know what people are thinking about when they look at these quizzes. So, and luckily, I mean, one good thing about the quiz, like an 80% score on a quiz with 5 questions, it's pretty good. I tricked on average, I tricked everybody one time. And let me also just see if I tricked anybody none of the time. So one thing that always worries me is if I tricked everybody one time. So we have a pretty good spread. We've got, okay, that's good. Let me look at it a little bit and think about it. I think I understand the way that you feel. I think that moving together is really what the covariance is doing. And it is a way that in which the variables relate to each other.
But that's not just together. It's how they relate to each other and how they move, like in relation to each other, right? It's not just them being together. It's like, does that make sense?
I mean, I understand the words that you're using. I don't see the difference between the two ways that we're describing it, but I feel like I'll think maybe more clearly in with a little bit of quiet.
Okay.
But I just appreciate knowing how you're reading this.
Okay.
Okay, and let me just also check here. Yeah, and I also like, I would kind of think of a 4 as like 100%. Like I'm not. There's going to be some curving in the class, and if you're and these are really kind of opportunities to check your knowledge and see questions. They're not. I'm not really going to give you a 79% or an 80% if you miss one question. There's going to be. I'm excited and glad for you if you get an 80%. That's a good score on these quizzes. If you get a 2, I'm kind of worried. I think that I'm failing, they're failing, we together are failing, and we need some course correction. So I think that and then a 3 I think is like you're doing great. You're like, it's obvious you're paying attention. It's obvious you're working, and it's just we need to kind of fine tune some of the material, some of our engagement with the material. But I'm not worried about someone that's getting a 3 or something like that. I think that one confused me too, because in the slides it says covariance is how much 2 variables change together, and correlation is a measure of how much variables change together. So they're both measures. I understand why that's confusing, but they are both measures of how 2 variables are moving together, whether when one moves up, when one moves into more positive directions, the other moves into more positive directions, or when one moves into more positive directions, the other moves into more negative directions. So they're really the related measures of the same thing, which you can see in part because correlation it includes covariance. So to calculate the correlation, it's going to be a function. It is actually the covariance normalized by the standard error of X and Y. Yeah, I know. Yeah, there's just a lot going on in terms of some of these new concepts. So I understand that they are prone misunderstanding, and I am trying to do as best as I know how to make them as clear as possible. What should be omitted since it wasn't clear enough? Yeah, thanks, Kimberly. Thanks for expressing that. I appreciate that. Okay. I'm going to look at it. If that question, more people got that wrong than right, maybe I'll throw that out. I'll go look at that. Other questions on the material?
The midterm is it's 25 points, but is it 25 questions or is it like?
The midterm will be about 50 to 60 questions, and in about an hour and a half, I think. So I think it will be 50 questions in an hour and a half. The purpose of that is I really want you to know the material before the exam begins. I really want you to not wait until the exam begins to start trying to understand the material. And the only way I know how to do that is to say, you got to know the material so well that you're only checking things in your notes. You're not trying to learn the material as you're coming to questions.
You said an hour or hour and a half?
Hour and a half.
Thank you.
Yeah, my pleasure. Yeah, I'll go through and go through the exam today, and you can use your calculator. You can use your notes. I think that you can use the slides, but in that time period, you won't have the time to dig through. We have hundreds of slides, so I just don't think that you'll be able to find what you need if you're going question by question into the slides. Yeah. Honestly, I think you're going to do well. And you should just know that this is a challenging class. There's no way around it. I teach this. Laura Giuliano used to teach this. Jesus teaches this as well. And it's just no matter what you do, it's a little bit hard because it's foreign, because it's a class unlike classes that you had before. So it does take an additional attention and an additional kind of settling. It's not the kind of thing that you can kind of like, if you read, I feel like if you read a psych textbook, I can consume a psych chapter in like an hour, and I know everything in that chapter that can be tested. This is a little bit different because there's math and the concepts are connected through math, and there's just a lot of conceptual stuff that's a little bit trickier to settle in your body. It's not just definitions and interesting studies. It's something kind of deeper than that. So it makes it harder. It also makes it more powerful and more useful in your life. More flexible. It's a toolkit that you can go out into the world and understand things much better. So I'm going to, class is dismissed. It's noon. I'm going to hang back and take questions, and yeah, feel free to get along with your day, and I look forward to seeing you on Monday. Please email me if you have questions. Please email me if you want to meet. And thanks, Derek. Thanks, Manuel. Stephanie, have a great weekend. I hope you enjoy it. Study hard, take a break, get a lemonade, and enjoy, take a break, do a hobby, call your mom or something. You too.
Professor, I had a quick question. So
Sure.
for all these formulas, they're when we do them for like other organizations, it's just you use data and whatnot because it's too much data, right, to collect. But pretty much this is just the fundamentals of it, right?
Yes. So you could do it mathematically, but you would normally be using Stata. It's just super important to know what Stata is doing in the background. Yeah.
This could work for like small samples, like collecting data around the block, right? And then just analyzing it, right?
Exactly. You wouldn't do this math probably by yourself on anything yeah, you would be farming it out to Stata or R or Python or something like that.
Yeah. Okay. So you think it should be pretty simple, right? Just pretty much review of what you've done in class, right?
I think so. Yeah, I mean, I think like, and if the quizzes are making sense to you, that's the kind of style of the questions in the on the test as well.
Yeah, it's kind of just questions on like review of the content. But I'm pretty sure like you already answered already, but I'm still unclear about the math questions. Just gonna be math questions, right?
So there are math questions, but they're pretty simple. Like, so I'll give you 4 data points and I'll say, calculate the mean X, calculate the mean Y, calculate the covariance between X and Y, calculate the correlation between X and Y, calculate beta naught, calculate beta 1, all using this data set, this small data set. So it's pretty, I think it's pretty, I don't think that you'll see anything on the test that surprises you. I think everything will look like examples we did in class, examples we did in homework, and not just examples, but things that we've done 3 times, things that we've done, you know what I mean? Like and if the quizzes are making sense, I didn't look at your quiz, but I didn't notice